Have you ever, promised to help a friend move, only to show up at their apartment and realize your car is just way too small?
Oh, absolutely.
And, you only have maybe 2 hours before you need to be somewhere else?
It is honestly a terrible feeling. You're just standing there on the sidewalk staring at this massive sectional sofa that mathematically will not fit into the back of your hatchback.
Right.
No matter how aggressively you try to pivot the thing.
Yeah. No amount of Tetris skills will save you there. And in that moment, you are experiencing what's called a classic capacity failure.
Exactly.
You promised a result without actually having the physical means to deliver it.
Right.
And letting a friend down is bad enough, obviously, but in the supply chain world, promising what you can't physically deliver, it literally destroys entire businesses.
It really does. It's one of the most critical, yet somehow underappreciated aspects of running a successful operation. I mean, we see companies go under, not because they had a bad product necessarily, but because they completely misjudged their ability to actually make that product scale.
Which is exactly why today's mission for this deep dive is unpacking something called capacity and production activity control.
That's right.
We're pulling this from our latest stack of supply chain management sources to explore how massive organizations, figure out what they can actually produce, how they measure it, and how they fix it when things inevitably go completely off the rails.
Because maintaining proper capacity is, well, it's essentially a massive financial tightrope.
A tightrope.
Yeah, think about it. If you have too little capacity, you end up with stockouts. Customers go elsewhere, and you just lose that revenue forever.
But then if you overcompensate.
Exactly. Building too much capacity means you just bleed profits. You're paying for wasted labor, idle machinery, empty warehouse space, you name it.
Right. So to avoid those massive financial losses, companies can't just, guess what their factories can handle when they wake up on a Monday morning?
No, definitely not.
They have to plan. And looking at the framework in these sources, that planning happens in 3 distinct layers, starting from years in advance all the way down to the daily shop floor.
Because you certainly can't turn a massive manufacturing operation on a dime.
Yeah.
So the first layer is long-term, which the industry calls resource planning. And this is looking, 1 to 5 years ahead.
Okay.
At this stage, you aren't looking at individual items. You're looking at aggregate demand for broad product families. This is where a company makes major capital investments like deciding to build an entirely new manufacturing plant in another country.
Right. So if I'm a CEO and I know demand is spiking in 2 years, I have to decide, when to actually pour the concrete and build that physical factory.
Exactly.
The sources highlight 4 specific staging strategies for this long-term growth. And reading through them, it really reminds me of trying to buy a house when you're planning to have a family.
Oh, I like that. Let's run with that analogy.
Okay.
So the first approach is the one-step lead strategy. You expand your capacity all at once, way ahead of the actual demand.
Right. So that is exactly like being a single person who goes out and buys a massive 5-bedroom house today, just assuming you will eventually get married and have 4 kids.
Yeah, exactly. It's high risk. You are paying a huge mortgage on empty rooms, just hoping the family eventually materializes.
But if the demand does hit,
then you are perfectly positioned to capture all of it without breaking a sweat. You've got the space ready to go.
Makes sense.
Now, the second approach is the stepwise laid strategy. Here, you expand in smaller, incremental steps, keeping just slightly ahead of the demand curve.
Okay, so that's like buying a 2-bedroom house and then adding a new room onto the back right before your next kid is born.
That captures the idea perfectly. You're leading, but just by a little bit.
Got it.
Then the third option is the stepwise lag strategy. And this is the complete opposite of leading. You wait for the demand to actually materialize and exceed your current capacity. And only then do you expand in steps to catch up.
Oh, wow. So which means you're basically waiting until you have 3 kids sharing 1 tiny bedroom before you finally decide to, build an addition.
Yeah, pretty much.
You're definitely sweating a bit. Your customers might be dealing with some back orders, but you are absolutely sure you aren't wasting a single dollar on an empty factory.
Exactly. It minimizes your financial risk, but maximizes your customer service risk. And finally, there's the stepwise overlapping strategy.
Right.
And that's where your incremental expansions alternate. Sometimes you're a little ahead of the forecast, sometimes a little behind, but it just sort of averages out over the long run.
Okay, so that covers the horizon looking 5 years out.
Yep.
But Once you have that massive factory built, you have to figure out what you're doing next quarter, which brings us down to the medium-term layer rough cut capacity planning, or RCCP.
Right. So rough cut capacity planning exists to check the master production schedule.
And before we go further, the master production schedule, or MPS, that's basically the factory's ultimate to-do list, right?
Exactly. It states exactly what end products need to be built and when. So RCCP takes that master to-do list and does a quick sanity check to make sure the factory can actually handle it.
Okay, so if resource planning is deciding to buy an RV for a cross-country trip years in advance, RCCP is checking the map the week before to look for major mountain passes.
That's a great way to put it.
You're just looking for the obvious obstacles you might not clear. But I actually found something really counterintuitive in the text here.
Oh, what's that?
It explicitly says that rough cut capacity planning only looks at bottlenecks and critical resources.
Right.
It doesn't check the capacity of the whole plant. Why on earth would you ignore the rest of your factory during planning? I mean, isn't that insanely risky?
It feels risky, I know, until you look at the underlying physics of a production line.
Yeah.
A bottleneck is simply the narrowest point of any system, right? It dictates the absolute maximum speed of your entire operation. So RCCP operates on this rock-solid premise that if your bottleneck, your most constrained critical machine, can handle the scheduled workload, then all the non-bottlenecks naturally have more than enough capacity to keep up.
Oh, I see.
Yeah. Checking every single non-critical machine at this medium-term stage is just a total waste of planning time.
So you only worry about the narrowest bridge on the road trip, because if the massive RV fits through that, it will fit through literally everything else.
Precisely.
Okay, that logic tracks perfectly. Which brings us to the third layer, the short-term horizon, capacity requirements planning, or CRP.
And this is the most detailed, granular level of planning. It happens during the material requirements planning stage.
Or the MRP.
Yep. If the master schedule was the broad to-do list, material requirements planning, the MRP, is the incredibly granular recipe. It calculates every single screw, bolt, and subassembly needed. CRP takes that massive recipe and translates it into specific standard hours of work for every individual work center. It checks open orders, planned orders, the routing files that show exactly the path a part takes through the building, and the specific work center files.
So finishing out the road trip analogy, CRP is calculating your exact gas mileage hour by hour based on the specific weight of the RV and the steepness of the exact hill you were driving up today.
It is the ultimate reality check before the real work begins.
But, you can plan all you want from a nice air-conditioned corporate office using those three horizons. Eventually, Monday morning arrives, and those plans have to survive the physical factory floor.
And they rarely do without a fight.
Exactly. Machines break, people call in sick, and that is where we leave the realm of pure planning and enter the second major theme of our sources, which is production activity control, or PAC.
Yeah, production activity control is just pure execution. The corporate planners have handed down the schedule, and now the PAC team has to actually make it happen.
Right.
Their objectives are to execute that master schedule, make the absolute best use of the physical resources standing in front of them, maintain customer service, and minimize what the industry calls work-in-process inventory.
Right. Work-in-process, or WIP, being all those half-finished products just sitting in piles on the factory floor tying up cash.
Exactly. It's capital just sitting there doing nothing.
So to manage all of this, you have to be able to measure what your factory can actually do on a random Tuesday. And the sources break down how to calculate something called rated capacity.
Yes, it's a specific formula.
Right. It is a formula, but I really want to ground this in reality for you listening. Let's picture a massive robotic welding station on an automotive assembly line.
Okay, great setting. So the rated capacity formula starts with available time. Let's say you have a work center with 4 robotic welders.
Okay.
And they're scheduled to run for an 8-hour shift, 5 days a week. 4 welders times 8 hours times 5 days gives you 160 hours of available time.
Right, 160. But no factory on Earth actually gets 160 hours of pure, uninterrupted welding out of 160 available hours. I mean, reality just gets in the way.
It always does.
So the formula requires you to multiply that available time by utilization.
Right. And utilization is just the percentage of that available time those welding robots are actually striking an arc and doing real work.
And why would it be less than 100%?
Well, the robots need preventative maintenance, right?
Yeah.
The welding tips need to be swapped out. The human operators monitoring them need their union-mandated lunch breaks. Because of all that real-world stuff, your utilization might drop to, say, 85%.
Okay, but there's still one more variable dragging that number down, right? Efficiency.
Yep, efficiency.
Yeah.
And this compares your actual output to the standard expected output, because even when the machine is running, is it running perfectly?
Probably not.
Exactly. Maybe the middle blanks delivered today are slightly thicker than usual, so the weld takes a fraction of a second longer. Or maybe the human operator feeding the machine is a new hire and just moves a little slower. Because of those factors, let's say your efficiency is running at 90%.
So, taking all of that into account, the math is brutal, but it's honest. You take your 160 hours of available time, multiply it by 0.85 for utilization, and then by 0.90 for efficiency.
And you end up with 122.4 standard hours.
Got it.
That 122.4 is your rated capacity. It is what the math says you should realistically be able to accomplish.
But then we have to contrast that rated capacity with another metric, demonstrated capacity, right?
Yes, and this is crucial. Demonstrated capacity throws the math out the window and just looks at the historical truth. It's the real-world average output over a set period of time.
So regardless of what the utilization and efficiency formulas say you should be able to do.
Exactly. If you average out your last 6 weeks of actual output and you only produced 110 hours of work, then 110 is your demonstrated capacity, period.
Okay, I want to pause on how these sources discuss measuring all of this, because they make a very firm point that capacity is never measured in money.
No, never.
It's measured in standard hours, or widgets produced both shift, or even available beds in a hospital if you're in healthcare. But never dollars or euros. And I have to ask, why wouldn't a business measure its core capacity in currency? I mean, literally everything else in a boardroom is measured in dollars.
It seems strange at first, but money is actually a terrible metric for physical capacity because currency is, well, it's a hallucination that fluctuates wildly based on external factors.
What do you mean?
Exchange rates shift globally, inflation rises, the cost of raw materials spikes. If you measure your manufacturing capacity in euros, a sudden drop in the value of the euro might make your spreadsheet look like your factory lost 10% of its capacity overnight.
Oh, wow.
Yeah, even though those robotic welders are producing the exact same number of car frames, it's just a financial illusion.
That is wild. So standard hours give you a pure, unclouded view of what a machine or worker can actually do. It separates the physical reality of the concrete factory floor from, like, the whims of the global stock market.
Exactly. Time and output are objective realities.
Mm.
A standard hour of labor is a standard hour of labor, regardless of what the Federal Reserve is doing with interest rates.
That makes perfect sense. Okay, so as a manager, you have done this math. You compare your true physical capacity to the actual amount of work the corporate office scheduled you to do this week, and you realize you have a massive gap.
Right.
The scales are completely out of balance. Say your factory is scheduled for 150 hours of work, but your demonstrated capacity is only 120 hours. What is the move here?
Well, when faced with this imbalance, a manager essentially has two main levers they can pull. They can either change the capacity to meet the load, or they can change the load to fit the capacity.
Okay, changing the capacity sounds like trying to magically create more hours in the day. How does that work in practice?
You literally add more work hours to the shift. The most common lever is scheduling overtime. You pay people time and a half to stay late and finish the 150 hours of work.
Right.
Alternatively, if you have the opposite problem and too much capacity, you schedule undertime and send people home early.
Oh, got it.
Another method to change capacity without paying overtime is changing the routings.
Meaning you just physically move workers around the building?
Yeah, basically.
Yeah.
You divert the flow of work to take advantage of underutilized stations, or you take cross-trained workers who happen to be sitting idle in one department and march them over to the department that's drowning in work.
Okay, let's look at the second lever. What if you absolutely cannot change the capacity? Like the union won't allow overtime and no one is cross-trained. You have to change the load.
Right. You have to reduce the burden on the factory floor. One way is subcontracting. You take that extra 30 hours of work and pay a third-party competitor to manufacture it for you. Another option is changing your lot sizes. So, altering the quantity of items you process at one time to try and squeeze out a little more efficiency.
Yeah.
And as an absolute last resort, you change the schedule.
Which means calling your biggest client, swallowing your pride, and telling them their order is going to be late.
Yep. Which is the nightmare scenario you're trying to avoid at all costs.
Listening to this menu of options, honestly, subcontracting to a third party or constantly paying your workers time and a half for overtime, It just sounds incredibly expensive.
Oh, it is.
If you were managing a facility right now, wouldn't it just be safer to permanently run your factory with, say, 20% extra capacity built in just in case? I mean, think of it like keeping a spare guest room in your house just in case someone drops by.
I get the logic. Having a safety buffer sounds comforting.
Yeah.
But in supply chain management, chronic overcapacity is a death spiral.
Wait, really? A death spiral?
Absolutely. Maintaining idle labor, powering equipment that isn't running, paying rent and heating for warehouse space you aren't actively using. That is a massive constant drain on profitability. It's just a hidden tax on your entire operation.
Oh, I see.
True efficiency isn't about having a comfortable safety net of excess. It's about finding the absolute perfect balance.
Which is why the sources place such a heavy emphasis on load leveling and capacity smoothing. You have to spread the work out evenly over the month so you don't have massive spikes requiring overtime, followed by terrifying dips where everyone is just standing around doing nothing.
Exactly. You want the entire system humming at a steady, sustainable rhythm. Spikes and dips destroy profitability.
But let's be honest, balancing load and capacity week to week feels like daily firefighting. You know, you're just trying to survive until Friday.
Right.
How do organizations structurally upgrade the factory so that tomorrow is actually easier than today?
Well, transitioning from daily firefighting to long-term structural upgrades requires a shift into continuous improvement methodologies. And the sources highlight two incredibly influential philosophies here: the theory of constraints and Kanban.
Okay, I want to dive into the theory of constraints, or TOSI. This was developed by a physicist turned management guru named Eliyahu M. Goldratt. And the core premise is brilliantly simple. Every single system on Earth has at least one constraint.
Right, a bottleneck.
Right, think about your own workflow at your job right now. You probably have a bottleneck you deal with every Tuesday. You know, that one specific software program that takes 10 minutes to load, or that one manager who has to personally approve every single document before it goes out.
Exactly. And Goldratt laid out a very specific 5-step process for dealing with those constraints.
Okay, what are they?
Step 1 is simply to identify it. Find the manager who is holding up the documents. Step 2 is to exploit the constraint. And that means you make absolutely sure that bottleneck is never, ever sitting idle.
Because an hour lost at the bottleneck is an hour lost for the entire factory, right? You can never get that throughput back.
Spot on. Then step 3 is to subordinate everything else to the constraint.
Subordinate?
Yeah. Every other machine or every other worker in the office should only operate at a speed that serves the bottleneck. There's no point in them working faster.
Makes sense.
Step 4 is to elevate the constraint. This is where you finally crack open the company checkbook and spend money to buy a faster machine or hire an assistant for that overworked manager to fix the bottleneck permanently.
And step 5, repeat the cycle. Because the moment you fix that bottleneck, a new one will naturally reveal itself somewhere else in the system.
Always. Now, the sources also mention a critical tactic here, which is putting a buffer, a small inventory queue, right in front of the constraint.
Okay, why is that so important?
A time buffer ensures the constraint never starves for work. So if the machine immediately preceding the bottleneck breaks down for 10 minutes, the bottleneck can keep running seamlessly because it has a small, deliberate pile of work waiting right in front of it.
There is an analogy for the theory of constraints that crystallizes the whole concept for me. Think of a factory like a massive highway traffic jam.
Okay.
The bottleneck is the car accident blocking 2 lanes up ahead. If you speed up the cars headed into the jam, it doesn't help anyone get home faster. It just makes the line of stopped cars longer, faster. You have to fix the blocked lane.
That's a perfect analogy. Speeding up non-constraints just creates excess inventory, which is the physical equivalent of a massive traffic jam on your factory floor. It ties up cash and hides defects.
Which ties perfectly into the second continuous improvement method, Kanban and visual signals. This is all about moving to a pull system.
Yeah, exactly. In a traditional push system, a central planning office looks at a forecast, guesses what customers might buy next month, and just pushes raw materials into the factory to start building it.
Pushing it whether they need it or not.
Right. And it very often leads to massive overproduction because, let's face it, forecasts are usually wrong.
Always wrong.
Kanban flips that dynamic entirely. It is a pull system. Work centers only pull inventory from the previous station when they actually need it.
The sources give a fantastic real-world example of this from Harley-Davidson. Imagine standing on their factory floor. You don't start welding a motorcycle gas tank just because a spreadsheet told you to.
No, you don't.
Harley uses special physical containers for their components. When a worker empties a container, that empty bin is the literal visual signal to the upstream supplier that they need more parts. No one builds anything until they physically see the empty bin.
And connecting this to the broader lean manufacturing philosophy, the ultimate goal is the relentless elimination of waste. By switching from push to pull-buy, relying on actual Kanban signals instead of corporate guesses, you eliminate the waste of overproduction.
Wow.
In lean thinking, overproduction is considered the most toxic of all wastes because mountains of extra inventory hide all the other systemic problems in your factory.
Man, we have covered some serious ground today.
We really have.
We started by looking at how organizations plan their capacity horizons, zooming from 5 years out down to the hour. We got into the weeds on the messy reality of the factory floor, calculating rated versus demonstrated capacity, and why we measure an objective time, not fluctuating dollars.
Right.
We explored the levers managers desperately pull to balance the scales when load exceeds capacity. And finally, we looked at how the theory of constraints and Kanban pull systems structurally upgrade operations to eliminate waste.
It really highlights the massive amount of invisible math and coordination happening behind the scenes of every single product you purchase.
Absolutely.
But, I want to leave you with a final thought to mull over. We talked about those physical Kanban cards and empty bins at Harley-Davidson serving as visual signals to pull inventory.
Yeah.
But as global supply chains become entirely digitized, driven by real-time tracking, RFID tags, and predictive AI algorithms, what will the visual signal of the future actually look like?
Will there even be a visual signal?
Will the factory floor eventually run itself without a human needing to see an empty bin at all? I mean, when the digital twin of a factory perfectly mirrors the physical one, the signal to produce more might just be a line of code executing silently in the cloud.
The invisible physics of the factory becoming truly invisible. I love that. Thank you so much for joining us on this deep dive. The next time you promise to help a friend move a sofa or you find yourself stuck in a highway traffic jam, take a second to look for the invisible bottlenecks in your own daily life.
See if you can't elevate your own constraints.
Exactly. Until next time.